Imagine you're trying to measure the exact timing of a spark plug firing in a high-performance engine,
Right.
and you need to measure it down to the literal microsecond.
Which is pretty standard for that kind of tuning, yeah.
Right. But here's the catch. The moment you add a line of code to actually measure and report that timing, the system delays the spark by 5 milliseconds.
Oh, wow. Yeah, that's a massive delay.
Exactly.
Yeah.
So the engine misfires, or, maybe it's a drone and the drone crashes, or a robotic arm suddenly stutters.
Yeah.
By simply trying to observe the system, you have fundamentally broken the system.
It's the embedded systems equivalent of the observer effect in physics.
Yes, exactly.
Because you absolutely need perfect visibility into the software, right?
Yeah.
But the tools that we traditionally use to get that visibility, they introduce so much latency that they alter the very behavior you are trying to study.
It's maddening. And that is exactly why we're here. Welcome to today's deep dive.
Glad to be here.
We are digging into a highly underrated, literally zero-cost hack for embedded systems today. It essentially gives you a cloaking device for your code.
That's a great way to put it, yeah.
In firmware circles, it's colloquially known as the free print statement. And our mission today is to look really closely at the mechanics of this.
Right, specifically contrasting the traditional painfully slow method of serial port printing against a much more elegant technique.
Using a synchronized memory buffer.
Exactly.
Yeah.
Accessed via the chip's debug port.
So whether you are new to embedded systems, or maybe you're prepping for a technical meeting, or you just love insanely clever engineering tricks, this is for you.
But we should probably clarify something right away. When we use the word free here, we have to define our terms immediately.
Right. We're not talking about, free software or monetary cost.
No, obviously not. We are talking about CPU cycles, computational cost.
Got it.
Because this technique allows a microcontroller to dump thousands of characters of diagnostic data without interrupting its core real-time tasks.
Which completely inverts how developers usually approach hardware debugging, right?
It does. It forces a complete psychological shift in how you write software.
Mm-hmm.
But to really understand why a memory-based buffer is so revolutionary, you have to look under the hood of what engineers have relied on for decades.
The dreaded UART bottleneck.
Yes, the UART bottleneck. The contrast is really what highlights the engineering here.
Okay, so let's get right into that baseline then. The traditional landscape, let's unpack this. If I'm writing firmware for a microcontroller, say, I don't know, a Cortex-M chip running a temperature sensor,
Sure.
and I want to print a simple debug message like temperature critical, how is that data physically getting out of the chip and onto my monitor?
Well, for the vast majority of the history of microcontrollers, the answer has been a UART.
Right, a universal asynchronous receiver transmitter.
Exactly. It's a dedicated peripheral inside the chip that takes data from the processor, formats it, and just shoves it out over a physical wire.
Usually converting it to something like RS-232 or USB via some external bridge on the board. So we are literally pushing actual electrons across a physical medium.
Yes, and that physical reality is the root of the entire problem. Because UART is asynchronous, meaning there's no shared clock line between the sender and the receiver.
They just sort of wing it?
Well, not wing it, but the two sides just agree ahead of time on a speed. The baud rate.
Right, right.
And frankly, by modern processing standards, even a fast baud rate is glacially slow.
Okay, let's do the math on that, because
Yeah.
I think people hear 115,200 baud and they think, wow, that sounds incredibly fast.
Yeah, it sounds fast until you map it to the processor's internal clock.
Okay, walk me through it.
So at 115,200 bits per second, you have to remember that a UART needs framing.
Framing, meaning like extra bits.
Yeah. To send 1 byte, which is 8 bits of actual data, you have to add a start bit to wake up the receiver
Okay.
and a stop bit to signal the end.
So every byte actually takes 10 bits on the wire.
Exactly.
Right, so let me do the math. 115,200 divided by 10 that's 11,520 bytes per second.
Spot on. So transmitting one single character takes about 86 microseconds.
86 microseconds.
Now let's put that in context. A standard modern microcontroller might be running at 100 megahertz.
Okay.
That means the processor core is executing an instruction every 10 nanoseconds.
Oh, wow. Okay, so in the 86 microseconds it takes to push just the letter T out the physical door.
The processor could have executed 8,600 instructions.
That is insane for one letter.
Right. And if you are trying to print a 20-character string, like your temperature critical example,
Oh, yeah.
you are looking at roughly 1.7 milliseconds of transmission time. That's 170,000 wasted CPU cycles for a single brief debug message.
170,000 cycles.
Yeah. The core is essentially acting as a burden messenger. It has to take the data, hand it to the UART peripheral, and wait.
Wait, I want to push back on that wait part. If the UART is a dedicated hardware peripheral, why does the CPU have to sit there and wait? Like, why can't the CPU just hand the string to the UART and go back to running the temperature calculations? It sounds like forcing the CEO of a massive company to pause running the business so they can personally hand deliver a single piece of mail to the post office.
I love that analogy.
Yeah.
And you're right, it's a terrible use of resources. But the reason the CPU has to wait is because the UART peripheral typically only has a very small FIFO buffer,
Like how small?
maybe 1 or 4 bytes deep.
Oh, that's nothing.
Exactly.
Yeah.
So once that tiny hardware buffer is full, the CPU has a choice. It can either block.
Meaning it literally halts execution.
Yes, it enters a while loop, constantly checking a status register to see if the UART is ready for the next byte.
That's agonizing.
Or it can use interrupts.
Okay, well, interrupts sound better, right? The CPU goes back to work, and the UART just taps the CPU on the shoulder when it needs the next letter.
Yeah, interrupts are better than blocking, but they come with their own severe latency penalty. Every time the UART finishes a byte, it fires an interrupt. The CPU has to stop what it's doing, save its current state.
Like pushing all its working registers onto the stack.
Exactly. It has to push all that onto the stack, jump to a completely different part of memory to run the interrupt service routine, feed one single byte into the UART, and then restore its previous state.
So you're trading a hard block for like 1,000 tiny paper cuts. The context switching overhead alone must be brutal.
It is brutal. The overhead of entering and exiting the interrupt takes dozens of clock cycles every single time.
Ow.
You're thrashing the CPU's pipeline and polluting its cache just to move a single character of text. It's an incredibly inefficient use of a highly advanced computational engine.
Going back to the CEO analogy, that's like the CEO pausing the company every 5 seconds to walk down to the mailroom and apply a single stamp to a single envelope.
Yes, but surely, you might say, embedded engineers figured out a way around the CEO doing the mailroom work.
Right. What about DMA? Because I hear direct memory access brought up all the time as the magic solution to UART bottlenecks. Doesn't DMA run completely in the background?
It's a very common assumption that DMA completely solves the problem.
But it doesn't.
Well, if you look at the actual silicon architecture, the reality is much more nuanced. DMA essentially acts as a dedicated mailroom clerk.
Okay.
You tell the DMA controller, hey, here's a block of 50 bytes in RAM. Feed them to the UART one by one whenever the UART is ready.
So the CEO hands off the whole stack of envelopes at once and goes back to work. That sounds like the problem is solved.
It mitigates the CPU wait time, yes, but it introduces bus contention.
Bus contention.
Yeah. You have to remember that the CPU and the DMA controller share the same internal highways, the bus matrix.
Ah.
They're both trying to access the same memory banks.
Oh, so they can crash into each other.
They don't crash because there's an arbiter managing traffic, but they do stall each other.
Ah, okay.
This is called cycle stealing.
The cycle steal.
Right. When the DMA needs to pull a byte of your debug text from RAM to feed the UART, it asserts a request to the bus arbiter. If the CPU is simultaneously trying to fetch a critical instruction or a data variable from that exact same RAM bank, the arbiter usually grants priority to the DMA.
Wait, really? Why does the DMA get priority over the actual CPU?
Because hardware peripherals are strictly timed. If the UART is starved of data, the transmission corrupts.
Oh, I see.
The CPU, on the other hand, can just freeze for a clock cycle, so the CPU stalls.
So the CEO still gets interrupted.
Yep. Furthermore, setting up a DMA transfer isn't free.
Right, you have to configure it.
Configuring the source address, the destination address, the transfer size, enabling the channels that takes dozens, sometimes hundreds of instructions.
Wow.
For a short 15-character debug print, the setup overhead for the DMA can actually consume more CPU time than just feeding the UART manually.
That's hilarious in a painful sort of way. So even with a DMA clerk, the CEO still has to draft the letters, organize the envelopes, brief the clerk, and deal with the clerk constantly clogging the hallway.
Exactly.
The system as a whole is still heavily taxed by the physical reality of moving electrons across a slow serial protocol.
The fundamental architecture is still rooted in the chip actively pushing data out a physical door.
Right.
And if UART and DMA are both bottlenecking the CPU and the internal buses, we need a back door. If the traditional way is forcing the CEO to be the messenger, we need a system where the CEO can just drop the mail in an outbox and immediately get back to work.
Which brings us to the alternative, The real meat of this deep dive.
Yes.
If we are completely abandoning the serial port console entirely, how on earth do we get data out of a sealed piece of silicon?
We use a wire that is already there. We repurpose the debug interface.
Okay, so we're ditching the UART wire completely.
Completely. In the ARM Cortex world, which, dominates the embedded space right now, this is usually the SWD.
The serial wire debug port. It's exactly.
For the listeners who might be familiar with older systems, is that like JTAG?
It is the modern evolution of JTAG, yeah.
Yeah.
JTAG required 4 or 5 dedicated pins on the microcontroller.
Which takes up a lot of space.
Right. As chips shrank and pin real estate became highly valuable, ARM developed SWD to accomplish the exact same deep silicon access using only 2 pins.
Just two.
Just 2. A clock line and a bidirectional data line.
Now, normally SWD is just used for programming the chip, right? Like when you compile your code on your laptop, you push the compiled binary over that SWD wire to flash it into the microcontroller's permanent memory.
That is its primary use, yes. Flashing and basic step-through debugging. But the SWD interface connects to a module inside the chip called the DAP.
The debug access port.
Right. And the DAP is incredibly powerful. It is essentially an independent master on the chip's internal bus matrix.
Independent master. What does that mean in practice?
It means it has direct access to the system memory.
Wait, meaning the debug probe can read and write to the chip's RAM directly without asking the CPU for permission?
Precisely. It uses memory-mapped I/O.
That is wild.
The debugger connected to your laptop can peer directly into the live working RAM of the microcontroller while the processor core is running at full speed.
Okay, so how do we leverage this for printing text? Because looking at RAM is one thing, but how does that replace print?
We completely changed the trajectory of the data.
Okay.
Instead of the CPU formatting a string and handing it to a peripheral to push out over a wire, the CPU simply writes the string into its own local RAM.
Oh, I see.
It stores it in a specifically formatted circular buffer.
Okay, let's break down that circular buffer implementation, because I know a lot of the magic happens in how that memory is actually organized.
Yeah, a circular buffer or a ring buffer is basically a fixed size array in memory.
Okay.
Let's say we allocate 1,024 bytes of RAM. It's called circular because when you write data to the very end of the array, your next write just wraps around to the beginning.
Overwriting the oldest data. So if you're listening, you might be thinking right now, if I just dump all my print statements into RAM, won't I quickly run out of memory on a tiny chip?
And that is exactly why it's a circular buffer. It never grows.
Right.
It occupies a strictly fixed footprint. You allocate 1 kilobyte once, and you reuse it infinitely. Now, along with that block of memory, the firmware maintains a write pointer.
A right pointer.
Right, which is just a variable that simply keeps track of the current index where the next byte should be stored.
Okay, I want to look at the actual computational cost of this compared to the 170,000 wasted cycles we calculated for the UART.
Let's do it.
If the CPU wants to print the word hello, what is it physically executing at the assembly level?
It executes a simple memory store instruction. In ARM assembly, that's an STR or STRB.
Store register byte.
Right. The CPU takes the character H, stores it at the memory address of the right pointer, and then increments the pointer by 1.
And how many clock cycles does that take?
Storing a byte to local RAM and incrementing a pointer takes maybe 2 to 3 clock cycles.
Wait, 2 to 3 cycles?
Yep. At 100 megahertz, that is roughly 30 nanoseconds.
30 nanoseconds, down from milliseconds.
Exactly. The processor is doing what it does best, right? Accessing its own tightly coupled memory.
Wow.
Doesn't wait for a baud rate. It doesn't check if a transmit buffer is empty. It doesn't configure a DMA channel.
It just drops the data into RAM and instantly moves to the next instruction.
This is why it is called the free print statement.
Uh-huh.
The CPU load is virtually zero. It costs the microcontroller almost literally nothing.
So by turning a massive physical bottleneck into a negligible memory operation, the limits of what a system can output shift from hardware constraints to simple RAM capacity.
Precisely.
Okay, I follow the speed advantage. The CEO is just dropping a note on their own desk and moving on.
Right.
But this raises a glaring technical question. The text is now just sitting in the chip's RAM.
Yeah.
It isn't being transmitted. So if the chip isn't sending the data, how does the text actually get to my screen without causing a traffic jam in the RAM?
This is where the magic of the debug access port comes in. The PC side does all the heavy lifting.
The PC side, so my laptop.
Yes. The software running on your laptop, usually a dedicated debugging server, constantly reaches across that SWD wire, uses the DAP to look at the exact memory address of your circular buffer and reads the data out.
So instead of the CEO walking to the post office, this is the PC acting as a messenger who quietly sneaks into the office, grabs the note off the desk, and delivers it.
I love that.
Yes, exactly. The CEO, the chip, just left the note and went back to work.
Right, the PC pulls the data asynchronously. The chip doesn't push, the debugger pulls.
How does it know there's a new note?
It reads the right pointer. It checks to see if the right pointer has moved, which means new data has been added. Then it copies the new characters over the SWD wire.
Okay.
And finally, it updates a read pointer in the chip's memory to acknowledge that the data was consumed.
Okay, wait. I'm spotting a potential collision here. If the PC is constantly polling the SWD to read the RAM, and the PC has to update a read pointer while the CPU is simultaneously updating the write pointer,
I see where you're going.
how does this not cause a massive data corruption issue? Don't they step on each other's toes?
That is a very critical engineering hurdle, but it is solved through atomic operations and bus architecture.
Atomic operations. Break that down for me.
Sure. First, let's look at the pointers. The read pointer and write pointer are separate 32-bit variables.
Yeah, okay.
On a 32-bit ARM architecture, reading or writing an aligned 32-bit variable is an atomic operation.
Meaning it happens in a single, indivisible hardware step?
Exactly. It cannot be interrupted halfway through. You can't read half a pointer while the other half is being written.
Oh, that's brilliant.
So you don't have to disable interrupts or use complex semaphores to protect the pointers. The CPU only modifies the write pointer. The debugger only modifies the read pointer.
They just read each other's pointers to calculate how much free space is in the buffer, but they never actually try to write to the same variable.
You got it.
That is elegant. So there's no software race condition. But what about the memory bus itself?
What do you mean?
Well, if the PC debugger is aggressively polling the RAM, like 100 times a second to see if there is new text, doesn't that flood the memory bus and stall the CPU anyway, kind of like what the DMA did?
That is where modern multi-layer bus matrices completely save the day. The CPU and the debug port are separate masters on the matrix.
Okay.
If the CPU is executing code from flash memory and doing calculations using its internal registers, the debug port can read the RAM simultaneously with absolutely zero contention.
Because they are accessing completely different physical blocks inside the chip.
Precisely. And even if they happen to access the exact same bank of RAM at the exact same nanosecond,
Well, does that happen occasionally?
it does. But when it happens, the bus arbiter simply interleaves the access. The CPU might stall for one single clock cycle, 10 nanoseconds, and then resume.
Which is totally imperceptible.
It is imperceptible. It completely isolates the active communication from the execution of the core logic.
This sounds like having a two-way mirror into your silicon.
It really is.
You are observing the internal state without shining a light into the room, which brings us perfectly to the biggest advantage of this method and honestly the most profound impact of this technique.
Right, avoiding timing distortion.
Yes. The Heisenberg problem of embedded engineering.
It's a very real problem.
I used the spark plug analogy earlier, but let's dive into a real-world scenario where a developer would actually hit this wall. Where does traditional logging completely ruin a system?
High-frequency motor control is the absolute classic example.
Like in drones.
Yes, drones, robotic arms, anything with a servo. You're likely using something called FOC.
Field-oriented control.
Exactly. To make a brushless motor spin smoothly, the microcontroller has to constantly read current sensors, run complex trigonometry calculations, and adjust the PWM signals going to the motor coils.
And it has to do this constantly, right?
Continuously.
Mm.
A typical FOC control loop might run at 10 or 20 kilohertz.
So 20,000 times a second.
Right. That means the processor has exactly 50 to 100 microseconds to read the sensors, do the math, and apply the output.
A real sweat.
If you miss that deadline, the motor vibrates, whines, or stalls completely. The whole system becomes unstable.
Okay, I see the trap here. So I'm the engineer. The motor is vibrating weirdly, and I want to know what the current sensor is reading right at the peak of the waveform.
Right.
So naturally, I drop a standard print statement into the middle of my 50 microsecond control loop.
And the moment you do that, your system crashes.
Because of the UART time.
Yes. We established earlier that printing a short string via UART takes a millisecond or more.
Right.
But your control loop deadline is 50 microseconds. By asking the system to report its state, you have blown past your real-time deadline by an order of magnitude.
Oh, man.
The system behaves completely differently when you observe it. The data you get back is totally useless because the act of collecting it broke the timing logic.
It's the ultimate catch-22. You need the data to fix the timing bug, but getting the data causes a timing bug.
Exactly. And this is where the SWD memory buffer approach feels like actual magic.
Tell me.
With a memory-based logger, when you ask for that current sensor value mid-loop, the CPU spends 30 nanoseconds copying the variable into the circular buffer.
Okay.
It increments the right pointer, and it immediately proceeds with the math.
It still has 49.97 microseconds left to finish the control loop.
Exactly. The motor keeps spinning flawlessly. The control loop is totally uninterrupted.
That's incredible.
And milliseconds later, at its own leisure, the PC debugger reaches in, grabs the data, and displays it on your screen.
You have achieved an honest measurement.
That's a great word for it, an honest reading. Because the reporting is entirely offloaded, the observation does not distort the data.
Here's where it gets really interesting to me, because this fundamentally shifts how you can trust your own tools.
It really does.
You mentioned earlier that changing the cost of logging changes a developer's psychology.
Yeah.
If I know that printing a variable only costs me 30 nanoseconds instead of a millisecond, how does that change the way I write code?
Well, it moves you from a mindset of extreme scarcity to a mindset of abundance.
Scarcity versus abundance. I like that.
Think about it. In the traditional UART workflow, debugging is a budget. You are constantly negotiating with your system.
Like, can I afford to log the temperature here?
Right. No, it might cause the USB stack to time out. I'll only log it if it goes out of bounds.
So you are guessing what happened in all those dark spaces between your sparse print statements.
Exactly. You're trying to piece together a puzzle with half the pieces missing because you simply couldn't afford to print the rest.
Wow.
But when you switch to an SWD buffer, which is often implemented using libraries like Sager RTT, by the way, that's kind of the industry standard for this technique.
Sager RTT, okay.
When you use that, the budget mentality disappears. It reframes what a debug print even is. It transforms from a costly transmission into a free note dropped on the way through.
So if it's free, I am logging everything.
You log everything. You log every state machine transition. You log the raw ADC values of every single sensor. You trace the exact execution path of complex algorithms.
Because there's no penalty.
Right. And if something fails, you don't have to try and reproduce the bug and add more print statements to see what happened. You already have a continuous, high-definition, honest stream of consciousness from the microprocessor leading right up to the crash.
That completely eliminates the endless fight with slow, blocking serial terminals. It must vastly accelerate the troubleshooting process.
It's a total game changer.
I am thinking right now, though, if I am logging thousands of variables a second inside a 20 kilohertz control loop,
Yeah.
won't I just wrap around that 1 kilobyte circular buffer instantly and overwrite my own data before the PC even has a chance to read it?
That is a highly relevant point, and it dictates how you configure the buffer in your software.
Okay, so how do you handle it?
When the buffer is full, meaning the right pointer has caught up to the read pointer, the firmware has two choices. It can either block and wait for the debugger to read some data, or it can simply drop the no message and move on.
Well, blocking would defeat the entire purpose. We just spent the last 30 minutes escaping the blocking UART.
Exactly. So in a high-performance scenario, you absolutely configure the library to skip.
To skip.
If the buffer is full, the print statement just returns immediately. You might lose a line of debug output, yes, but you absolutely protect the real-time integrity of the system.
Because the motor has to keep spinning.
Right, the motor keeps spinning. And often you can just dedicate more RAM to the buffer, maybe 4 kilobytes instead of 1, to absorb those high-frequency bursts of logging.
So what does this all mean for you, the listener? If you are going to go try this tomorrow, are there any common traps engineers fall into when setting this up?
Oh, definitely.
If it is this incredibly powerful, there has to be a catch or a setup hurdle.
The main hurdle is memory architecture awareness. When you set this up, you have to place a specific structure in RAM called the control block.
Control block.
Right, which holds the buffer itself and those read and write pointers we talked about. The PC debugging tool needs to know exactly where that control block is.
Well, how does the PC find it? Does it just scan the entire RAM?
It can. It can scan memory for a magic string, like the letters RTT followed by a specific byte pattern. But if you have megabytes of RAM, scanning takes time.
That makes sense.
So the better way is to explicitly tell your PC tool the exact hex address of the control block. A common mistake developers make is letting the linker script put the buffer wherever it wants, and then the PC tool can't find it.
Okay. You have to map the exact coordinates for the messenger.
Exactly. Another frequent error on advanced chips like the Cortex-M7, for example, involves cache.
Cache memory.
Yeah, these chips have fast L1 memory caches. If your CPU writes the debug string into the cache, but the data hasn't been flushed out to the main RAM yet.
Oh, the debug probe is looking at the main RAM and it sees nothing.
Exactly. The debugger pulls stale data.
Because the node is still in the CEO's pocket. It never made it to the desk.
Perfect analogy, yes. So developers have to ensure they either place the circular buffer in a non-cacheable region of memory, or they configure the hardware to correctly manage cache coherency for that specific memory block.
Right. But once you overcome these initial architectural setup steps, the workflow integration is pretty seamless.
Incredibly seamless.
So if we look at this from a high-level workflow perspective, what is the core hardware requirement to actually use this today? Do I need expensive proprietary gear?
Not at all. That is the beauty of it. You need a microcontroller with a debug access port that supports background memory access.
Which is how common.
It's virtually every ARM Cortex chip made in the last 15 years, as well as many modern RISC-V architectures.
Oh, okay.
And you need a standard debug probe, which most development boards already have built right onto the PCB anyway.
So the hardware is literally already sitting on your desk.
Yep. You just have to change the software routing. Instead of routing your print function to the UART peripheral registers, you use a compiler directive to route the standard output to the memory buffer API.
Yes. You just swap out the back end of your logging library. The front end code that the developer actually writes, like print, hello world, stays exactly the same.
Exactly the same.
But underneath, instead of triggering a 1 millisecond hardware cascade, it triggers a 30 nanosecond memory copy.
It is brilliant engineering.
It really is. Let's do a quick, energetic recap of how deep we just went, because this journey touches almost every layer of embedded architecture.
It does.
We started at the painful baseline, the asynchronous UART, a physical bottleneck where the CPU is forced to act as a messenger, wasting hundreds of thousands of cycles just to push electrons over a wire.
Right, and we looked at how even throwing a DMA controller at the problem only creates bus contention and setup overhead, leaving the system fundamentally constrained by the speed of the serial protocol.
Then we flipped the architecture. We explored repurposing the SWD debug port using memory-mapped I/O to access the chip's internal bus matrix without halting the processor.
And we unpacked the mechanics of the circular buffer, how atomic operations and separate read-write pointers allow the CPU and the debugger to interact with the exact same memory space completely asynchronously.
Without race conditions.
Exactly.
And most importantly, we saw how reducing the computational cost of an observation from milliseconds to nanoseconds solves the Heisenberg problem of firmware. It allows you to monitor violently fast, high-frequency control loops without distorting the timing deadlines that keep the system alive.
It frees developers to debug without limits. It moves you from debugging on a strict cycle budget to a workflow of complete high-definition visibility.
It really makes you look at every bottleneck in your system and wonder if there's a backdoor you just haven't noticed. Hardware debugging has a funny way of exposing how often we just accept legacy systems because, well, that's how it has always been done. If you are leaving massive amounts of insight on the table by still using a UART for your core debug logging, you are essentially forcing your CEO to walk to the post office.
And, I think there is a broader takeaway here that extends way beyond firmware.
Oh.
When you look at how systems scale, whether it is a piece of software, a team, or a massive organization, the most destructive friction almost always occurs at the interfaces.
Right.
In this deep dive, we've seen how offloading the reporting allows a microprocessor to do its actual job without distraction. When one highly efficient entity has to stop working to manually synchronize with a slow, external entity, the whole system degrades.
That is a phenomenal point. The solution wasn't to make the UART faster. The solution was to stop synchronizing entirely, to decouple the work from the reporting of the work.
Exactly. Design systems where the core engine just drops its status into a buffer and keeps running, and let a separate asynchronous process handle the delivery. It makes you wonder in your own life or your own teams, how much of your core valuable work is being bogged down by the equivalent of a slow, blocking UART terminal.
Where else could we just leave a note on the desk and get back to running the system? That is definitely something for you to mull over the next time you find yourself stuck waiting for a process to clear. Thank you for joining us on this incredibly deep dive into the silicon. Keep questioning the defaults, look for those elegant architectural backdoors, and keep exploring. We'll catch you on the next one.